Hi everyone, welcome to my channel. Today I basically want to go through and see what the difference is between shadows on a flat earth and shadows on a globe earth on miniature models. Here we have a ball represented by this ball. You have the equator, the North Pole. You've got 12 inches marked out on the ball. You got the Tropic of Cancer approximately where it is on the globe earth. The distance from the equator to the North Pole is about 6,225 miles. Each inch is about 519 miles. And Tropic of Cancer, 23.5 degrees north. So that's about 1,600 miles north from the equator. Same thing here with the flat earth model. We have the equator represented by the edge of this toy. Again, 1 inch increments all the way to the North Pole. The Tropic of Cancer off of the equator. I'm going to place a stick represented by this cap, and we're going to turn off the lights and see how the shadows behave. We're going to have a distant sun for the ball, and then we're going to have a localized sun for the flat earth, as the flat earth proponents claim the sun is local. So let's begin by turning off the light, putting in our first stick in the ground at the equator, and we're going to measure out and see what kind of shadows we get. So at the equator with a distant sun, there should be no shadows. There is a slight shadow. There we go. Let's move the earth down a bit. Okay, no shadows. At the first inch increment, centered, we have a small shadow. So we'll do from the center of the cap to the top of the shadow. This is position 1. Position 2, center of the cap, top of the shadow. This is position 2. Position 3, the shadow is increasing. This is still the same time of the day. 12 o'clock represented here from the center of the cap to the top of the shadow. This is position 3. Position 4, center of the cap, top of the shadow. I'll do a squiggly line for position 4. Position 5, sorry about the lighting. We'll turn the light on at the end. Position 5, center of the cap, top of the shadow is about here. Maybe turn on another light so you can see. Oh, you can't, because if I turn on the light, you can't see that. Never mind. Trust me. The top of the shadow is much longer than position 4. Obviously, this is 5. Position 6. The shadow has gone past the North Pole, or at least at the North Pole. Okay, let's move over. Position the localized sun. Turn on the lights for the local sun at the equator. There we are. Let's turn off the other light. I'm using the same cap. We're going to mark out the shadow. Okay, when the sun is directly above the earth, on a localized sun at the equator, there should be no shadows. Position 1 on the flat earth model, there is a small shadow, center of the cap. Position 2, the shadow from the center of the cap, this is 2. Position 3, center of the cap to the top of the shadow, this is position 3. Position 4, the shadow is increasing. Position 5, center of the cap, top. Position 6, center of the cap, to the top of the shadow. That's position 6. Position 7, center of the cap, top of the shadow. Position 7. Position 8, 519 miles up. That's position 7. No, that's position 8. Okay, position 9. And we have 9 and 10. 11. And at the North Pole, oh, did I do that wrong? 11, 12, 12. Okay, let's turn on the lights. So, what do we have here? As we increase on the globe Earth model, we move the position of the cap up. This was position shadow 1. This is the length of the shadow. At the equator, there was 0 shadow, a small shadow. The shadow increased position 2, increased position 3, 4, increased 5, increased 5, increased, and 6, the shadow went way past over the North Pole. Okay, and on the flat Earth model, what we have is 0 shadow at the equator, a small shadow position 1, small shadow position 2, bigger shadow position 3, bigger shadow position 4, bigger 5, 6, 7, 8, 9, 10, 11, 12. So the shadow doesn't increase exponentially on the flat Earth, but after a certain point, if each inch is 519 miles, then we're looking to see that after a certain latitude on the globe, the shadows would be extremely long. And this would definitely be in North America. And when we go outside, we don't see shadows that are that long. They're a little bit longer than the height of the object. So Eratosthenes' experiment claimed that the only way that we can get a shadow on the Earth from a distant sun is if we assume that the sun is distant and that we have therefore a curved Earth, or if we assume that the sun is local and the Earth is flat and the sun is above at the equator where there is no shadow, and we move up the same interval, different latitude, same time of the day, the shadow will increase, just not exponentially like the curve demands. Thank you for watching this video. Appreciate you taking the time. Please remember to like, subscribe, and leave a comment below. Thank you, and goodbye.